So what, like if you want to get aligned with what I am like what I am covering, you can follow Chester Rebellion from IIT Madras. So Chester and I was like many of the things that I am covering right now. Even Chester is covering probably in his lectures are aligned because we used to discuss about this. He was my roommate and we used to discuss a lot of different things. See, after just Chester Rebellion. Okay, guys, let us start. Guys who has joined from online, you are back.
Yes.
Okay, should we start?
Yeah.
Okay. You see the screen here, right? And please focus on the blackboard also. Now uh, we are going to learn Wigner cipher, which is kind of a modern cipher. You see a table here in the right hand side of the screen. There is a table, right? So it's similar to Caesar cipher, but Caesar cipher has a problem. It was type key, and it is very easy to understand that what is the key, and it is very easy to understand what is the substitution. Now Wigner did a little bit tweak on that. He said, okay, I will not use the same key for every letter. Screen is shared, right? I have to share my screen. Hey folks, you should tell me that I am not sharing the screen. Now you can see the screen. This one, right?
Yeah.
Okay, perfect. So this one, so Wigner did a little tweak on that. So he said for every letter I will have a different password. Anyway, for the Caesar cipher, the password is just one single number. He said I will change that thing. I will not use the same password for everything, same number for everything. So just focus on the blackboard now again. I will leave this spot. Okay, just give me one plain text. Any like small plain text, single English word, anything. I am good. I am good. Another single word in English. Anything. Excellent. Small one. Happy. Huh? Happy. 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 Now we will use this as a password, and this is the plain text. So this is the key and this is the password key. How? Now see this table. First key is H, right? This one is H. Will come here H. Okay? And then what is the plain text? I. In this row, come to I. I will be replaced by P. Sorry? H. No. Top. This is I. This is H. Where they are P. Because this is the plain text. This is plain text. This is the key. So this is the row and this is the column. This is the P. Sure? So P. For you guys who are online. So first letter is H of my key. Happy. First letter is H. You can see here. And the first letter of the plain text is I. So this column and this row is meeting at P. So P will be my substituted letter. Similarly, plain text is A and the key is also A. So it will be A. After that, M and P. Let's see. T and M. This is right. B. This is P and this is M. This is B or C? The B, right? Yes. Oh, I'm sorry. Laser pointed. This is P column, and the text is M, right? M is here. P and M meets at B. So this B I am taking. After that again, happy will keep repeating. Yes, it will keep repeating. Then again P and then B. Now, yeah, P and G, what will be? P and G will be V. Space is not included, right? Space is not included. Usually in the Morse code, nobody cares about the space. So is there any logic in the all of that? Sorry? Is there yes. Logic in that? It is just a shifting, like A, B, C, D, E, F, Z, then just shift one and put the A. It's actually shifting. Yeah, it is a left shift. Left rotation actually, not shift. Yes, what is the actual cycle? This metric will remain same. Metric will remain. Metric will remain same. But the password is the key will change. So if you do not know the key, you cannot. And for every letter, I am actually changing it. So it is very difficult for the other person to understand unless they know the key. So you can see this happy. This key is actually the rotor of the Lorentz machine. And this is the text. Like this is the same table, and the plain text will be converted to ciphertext. No way you can find it. Not possible. Even here are two O, right? P and Y. So P and O will be, let's see, P and O will be D, and then Y and O will be M. The beauty is, even though in the plain text this is repeating, here it is not repeating. Or even though here it is repeating, in the ciphertext it is repeating, that doesn't mean that the plain text is same. So you cannot do frequency analysis also. Right? You cannot do frequency analysis, you cannot guess unless you know the keyword. That's why it is always said you must change the rotor position. Otherwise you are doomed. That exactly thing happened. So this is how the Wigner cipher works. So Wigner created it in 1553, long back. It is a polyalphabetic, that means one alphabet, one letter can be represented into different ways. You cannot find any of the 26 key or passcode to be used, and it is thought to be unbreakable until 19th century. So we thought that this is unbreakable, this is the best cipher. But yes, normal frequency analysis didn't do a work here. Other things did not work here. But Kaiseki experiment in 1864, Kaiseki is another mathematician. He actually found a different way of treating. That is how the mathematicians work, right? This is a piece of art. So they work on that, and if you are interested, you can just read that text. So he has just taken some of the chunks and did some experiments, and he actually find out the keys. Like he find out how to attack on this. So it is not anymore unbreakable. Because 26 anyway, 26 letters, all the permutations he just tried and then found the pattern, then use the GCT because the mod is applied, all these things he did. He found this thing. So I'm not going detail into this cryptanalysis, but just to let you know that mathematicians try to find new mathematical tool or the new pattern analysis to attack, like to do a cryptanalysis on the newer things. So what is believed to be unbreakable today might not be unbreakable really. Some of the innovative mathematician, very smart mathematician might find a flaw in that system and they will find it. Okay. So now let us I probably this link I have shown you, and Wigner I just extend here. That is same thing. You can just try online. These are the two links I have given. The first one you can try the same thing. Whatever I have done, you can just try it in the on online to do just an application. And the second one is that This how the SCSI key. Now come to from the beginner. Once beginner is proved to be broken. So I have broken it.
And remote is not working, break it.
So one-time pad used to look like this. It was used in the World War. During from the First World War, even today also it might be used in places. So what it says, this password, like there is the problem here is the password is known, small password, and this is getting repeated. Like if the plain text is longer than the password, we repeat that password. So they said, okay, we'll implement it in a different way. Let's have a pad, writing pad, and we will keep on random. We'll write random letters on that. Keep on writing, page after page, page after page. How it will be implemented? There will be two identical notepads like this. Same pad. It is not computer notepad. The writing pad. Two same identical writing pad. One from to the receiver, one to the sender. Sender will send with the this will be the this endless string is the password. So the same Vigna cipher I will use with this one is as a password. The plain text I know, this one I know. I will from here I will actually this is just to circle on this thing, so that the the idea is you will circle the cipher text and then send the cipher text. Take this pad, first pad, the first leaf of the pad, destroy it, and it has to be done both ends. The sender will send, destroy that pad, the first page. Receiver receives, once it receives, send the destroy the first page. Then again, he said somebody. So always these two guys will be on the same page, because receiver also is destroying the page and the sender also destroying the page. So always they will have the same. They will be on the same page. They will have the same password. But only key is you cannot reuse this. One pad, one password is done. You have to destroy that page. First of all, that page contains contains the formula, like contains the ciphertext and the plain text. That is one thing. And secondly, if you reuse, somebody can break it. Just the way we have taken the beginner. Okay, simple. Done. One time pad. This is called one time pad. Till date, this is considered to be unbreakable. No one can break it because there is a random string. For every single letter, we are actually replacing it something else, and we do not know what it is because that is a random letter. Only the receiver knows, sender knows. But what is the problem in that? What is the problem? Tell me. Any problem do you see? The only problem is implementation. How many big pads will you carry? Every time you are sending one single word, a single letter even, okay, just or copy it. That single or that word also you are destroying one page. And how many fat book will you carry? Implementation is the problem. And secondly, doesn't matter how many times you tell them, people will reuse these. Because after some point of time, it is convenient to reuse the keys. Right? So it is very difficult to implement. Especially
That time it might be difficult, but now we can use a right rule system computers.
exactly that's what we are going to do. Exactly that's where our modern day ciphers sit. So this is proven to be unbreakable. This is the best crypto system we got, but implementation is very difficult. And second problem this has, you cannot resend a message. One message is sent, receiver could not understand. Then again you have to codify the entire message and again send. Right? And also like two-person on the same page would sometimes be difficult. You send a message, but message did not went to the receiver. Then receiver and sender will be on two different places. So implementation is very difficult. But this one actually was the best one, and in fact the soldiers used to use this one. So who usually do this in the dictionaries? There are different guys.
There are ciphers there in single basically. So your message will be given to single guy.
There is a dedicated guy.
Yeah. And there is very infantry also.
I feel pity for them. So
It is a small team, it will do it. Morse code they use a lot.
yeah, Morse code is there, but Morse code is also codified. Now from the Morse code you have to get the exact message. The plain text message you need to find. The Morse code is again codified like this.
I use simple cipher. I remember when I was there. Simple cipher within.
Okay, don't tell us mostly.
Very simple one.
Okay, that's a don't tell us. Okay, but yeah, this is thought to be the best one, and yeah, in the World Wars people used to use this. Yeah, when you are sending a strategy or something,
Yes, yes,
probably that is this kind of.
So within this room, if you have to discuss, we have a simple one. Like we have to meet there. Can we put it to Kalahati? Suppose. Okay, so that will also work, na? Within the team.
Exactly.
Some password will work, passphrase will work, something like that. So that's all. It depending on the use.
A strategic discussion will happen in a very Kalahati actually. Okay. This is breakable if keys are truly random. Okay, one more thing, the keys must be random. It's truly random. It should not follow a pattern. A, B, C, D, E, F, G, A, like A to Z, A to Z, A to Z, it will not work, right? So it has to be truly random. Keys are never reused and pads are kept secure. These are the things. And now another problem it has, like if somebody gets, the enemy gets gets access to the pad, then it's a problem. Then they can decipher everything. Okay, now this is not practical. Clearly, this is not a practical. Now we will use the same thing here. Exactly the idea that came to your mind. The great people also got the same idea. Let us implement it in the great people think alike.
Yeah.
Right? Great people think alike. Okay. So how we are going to implement it? Remember, we just learned XOR. So this is how we are going to do this. So plain text key we will XOR, we will create the cipher text. Without knowing the key, we can never find what was the plain text was. So let's come here. Okay, you remember 9 was the key and DF was my plain text here. Oh, sorry. Okay, remember we started with this one, this number, and this is the 0, like 9 was key and DF was my plain text message. Fine, and we have made the XOR. So the encryption perfectly worked. How about the decryption? Same. So this XOR has another beautiful property. So if you do the XOR twice, you will get the exact same thing back. So again, I am using the same key 1001 1001. I am making XOR. Will be the, tell me, 1 1. Is it the same where we started? So this is the beautiful thing that we have, and this is the key, and this using the same color. Okay, so using this one, if we have a endless stream of zeros and ones for doing the XOR, and we have a plain text between 0 and 1, we can perfectly implement one time stack. But the only problem, we need an endless string of zeros and ones. But again, we cannot do that. The same problem, right? Now what we can do? We will reuse the same key. Good. So this is a smaller one, 4 bit. This is 8 bit. I am just reusing twice. If it is bigger, I will keep reusing this one. The same key. Okay. So it is somehow implemented, but not fully. Again, the same problem is there. We are reusing the key. Fine. Okay. The same thing that I just shared the one-time pad with bits. Exactly the same thing that I showed. Symmetric if no. Now the problem. There are two things. One, if we reuse the same key, problem will be there will be a pattern in the in my in the plain text, in the cipher text. Because I am using the same key, there will be sometime people will find that pattern. We have to break that pattern. How we can break the pattern? What Claude Shannon said, there are two ways to break this pattern so that nobody can find it. Perfect law of perfect secrecy. What he said? Plain text and cipher text will be independent, and every bit of the key will have equal importance on the entire cipher text. This is the thing he said. Exactly, we are doing the same thing, achieving the same thing. First, what we are doing, we will simply not XOR the way it is. XOR output, maybe this is the output. We will put it not for the first. I will just send it in the, so some randomization I will do. This is again fixed. This is not like every time it is changing. This is fixed in the implementation. But I am breaking the pattern every time. So that the first bit will be, here I think it is the 6th bit. That means the block will be different. 4444 block is there. Now I am breaking that block, that pattern within one single, like, because every 4 bit is, my key is 4 bit, right? My plain text is 8 bit. So it is repeating twice. What will happen if one of the output, I will just send the output as this one. Simple. Then it will be broken. And again, another thing we have to break. What is that? So this is for the permutation. That means this is the plain text and the clear text. These two will be totally randomized. Every pattern will be broken. And inside this S box, we will break the pattern between the key and the cipher text. How you are going to do that? Again, we will do the same thing, but instead of doing simple XOR, we will just again randomize something. So this is 0, 1, 1, 0. Maybe this is like this is the XOR. After doing XOR, I'm just coming to this.
So how much was repeated?
We will follow the exactly opposite direction. Whatever, like first bit became the 6th bit. When decryption, we will do the 6th bit to first bit.
But that pattern has to be known to both.
That is known because implementation is known to everybody. Algorithm is known to everybody. It is known to everybody. Keys are the only secret. But from just the pattern, now you do not know the key. From just the pattern, it is very difficult to find out the key because you are doing S box and P box. Before the XOR, after the XOR.
XOR is also randomized. And the
Both
output
are
is
randomized. No, before the XOR, yes, actually you can implement that way. There is some implementation before the XOR key is getting randomized. Some implementation before the XOR plain text is getting randomized. Something both the randomization done after this.
First of confusion, next of diffusion.
Yes, that's first one is confusion. So Claude Shannon said confusion for the S box substitution, diffusion for permutation. S box and P box. Simple. Now we'll do that again. Another exercise here. Let us.
confusion is the confusion. अभी इसमें time कितना cost दिखाएगा वही. इसको diffusion भी रखे थे बनाने के लिए.
Okay. Let's take this example. Now this is our P box and S box. Say. Okay. So this is our S box. Guys, please here. I'm okay, guys. Let us see. So, how the S box is working? This is 0, 1, 2. This is the zeroth box, right? For our keys. For every 4 bit, this is the zeroth block. See? This is first. This is second. This is third. So the zeroth box input will go as a second box output. Okay. Should I use this? Okay. Now I can actually things. Now let us see. 0, 3, 1, 2. That's what it is. 0, 3, 1, 2. So now we have just give me a random binary number. Some 1, 0. Take that one.
Double 101. Okay.
Double 101. Perfect. Now it says zeroth bit will be the second bit. This will be uh, this will be the here. This will come here. This one is coming here. First bit will be the first bit. So this will come here. This one will come to 3. And this one will come to 0. Anyway, we are getting the same thing. Yeah, but you got it.
Anything like that in 1 second?
Before
Sure.
XOR. Before XOR, it is, sir.
Before XOR, after XOR, but sometimes you have to do that. There are different implementation. I will come to that. There are different implementation. Some implementation does it before, so it will create new and new ciphers. Some ciphers, some implementation did it before. Some implementation did it after. Some implementation did one like S box before, P box after. Some implementation said no, both the thing will be after. Somehow it is happening. Yes, I am explaining it one second. This is zeroth bit. This is first bit. This is second bit. This is third bit. This box, S box, is saying which bit will go where. Zeroth bit will be the second bit in the output. So this is S box. If I give 1, 0, 1, 0, 1, say, just another new number. So I will get an output. What will be that output? That output I will get it from here. So in this is the input. What is the zeroth bit of this input? This one, right? This one is the zeroth bit. This box is zeroth bit will go to the second bit of the output. So this is the output. This is the input. 0, 1, 2, 3. This is the input. Okay, got it? These are the bit position. 0th, first, second, third positions. It says 0th position will come to the second position. So this is the 0th position. We have 1. Here in the second position we will get 1 because 0th position will go to the second position. Then tell me first position. First will go to first. This is first. Where will I put 0?
First.
This one. Then this one 2 will go to 3. This is 2. which is 0. Here, this is 3. 2 will go to 3, so here I am putting 0. And third will go to 0. This one is 1. Understood? Perfect. This is S box. And P box is the bigger one. So P box will be bigger than the key size, of course, because reusing the key, I need to make that pattern. That's why it will be bigger than the key. So even though I am using 4 bit of key, if I take 8 bit, then what will happen? The first will go, say maybe what I have written 2751340. 275134006. Okay, so this is 0, 1, 2, 3, 4, 5, 6, 7, right? Now I am talking about the P box. Okay, so here I have given the example of 1001. Now let us take the same example. Our key size is this 1001. Oh, that's the same thing I said. Okay. So every time the key will be changed, but that will be a problem. If you do it before, the problem will be only key is getting changed. So instead of this one, the key will be changed, but same the repetition pattern will be there. So S box we should do it on the output, even though there are implementation which does before, but that you understood. Every time if I change the key, then instead of 1001, this 0101 will be repeating. The same repeating pattern will be there, right? So what will we do? We will actually use this output 1101. That's why we started. So 1101. Actually, here what I said, what we found, it will be the same 1101, right? So here S box doesn't have much effect. Then 1111. Then also the same thing will happen. So anyway, the S box did not work for this particular bit pattern, but you understood that different bit pattern will create different output, right? So we got what 11 here 1101 right? This is what we got. Oh no, sorry, I am using the plain text. I should use the cipher text only, na? Yes. So I'm sorry, you guys never told me that. This is the plain text. I am not doing it on the plain text. I am doing it on the cipher text.
P box on cipher text, right?
Both the thing will happen on the cipher text. For the timing of what I am explaining, everything I am doing on cipher.
0100.
Yes. So 0100. Tell me what will be the output? Please tell me the output. 0100. Zeroth bit will go 0. 0 will be 2. This is 0, right? This 0. And the second one is 0110. So the output here will be 1000. And the second one is 0110. What will be the second? 0 will go to 1010. Sure? I'm not checking it. 1010, everybody take it? Then I'm not calculating again.
0 will go to 2, 1 will go to 1, 1 will go to 3, correct.
Correct? 1010. This is the output. This is the cipher text. This is the cipher text. Now I first did the cipher text, put the S box. Now the entire cipher text to the P box. Now what will be the output? Tell me. This is 0, 1, 2, 3, 4, 5, 6, 7. Right? 0 will go 6th. 0th bit will go to 6th bit, 0. First bit will go to 0th bit, 0. No, sorry, 1. First bit will go to 0th bit, so 1. Then Second bit will go to fourth bit. Second bit is 0, fourth bit will be 0. Then fourth bit, right? Fourth bit will go to 1. Here is the fourth bit, it will go to 1. Fifth bit will go remain in the fifth bit. So fifth bit is 0. Then sixth bit will go to 7. Sixth bit is 0. 7 will be 0. And the seventh bit will go to 2. Seventh bit is 1. Like third bit is left. Third is okay. Third is 1. Okay. So this will be the output. Now everything is jumbled up. Everything is confusion, diffusion in say or H box, P box. H box, P box is the implementation for the confusion and diffusion. Now if you keep on doing all this every time,
Then there is any application that calculates the first to be used. So are there any applications that calculate?
yes, so this is the implementation is perfect. You understood this implementation. Coming to that. Okay. Okay. So S box, P box is clear. This is clear how we are doing this XOR operation. Fine. Now we have properly implemented the OTP with lot of different magic. We understood the magic. Okay. S box, P box by B with the S box. Okay, this one I have taken randomly, just a random thing generates. Every time I am creating my own cipher, I will generate this S box and P box, this, this combination. The different cipher uses different, and this is known to everybody. So some of the ciphers use like the way I have used. It is 24 cross 24. Every 24 bit will be taken. The 20 feet bit of 24 bit of the cipher text, and then they just change the pattern. Sometimes they do expansion. 12 bit is taken and they create 24 bits. Some of the bits will be random. Like every some of the bits will be repeating. Like if you see here, probably second bit has repeated, or yeah, 6 bit is repeated. See, 6 bit is repeated. So if you just repeat few of the bits, then you can expand. Or sometimes you can even compress. That is, you will just take part of that thing. Okay, but for compression there is there is a difficulty. Well, the cryptic, you might lose some data if you have not implemented it properly. That is the problem for the compression. So you understand ASP network, how the plain text work, how the cipher text work. This is the element of a P box. It actually happens. I will show you. It actually happens. The plain text is taken, goes to S box, P box, then XOR, key 0, key 1. Now the same key might be repeated. Most of the cases, so far what we understood, the same key we are keep on repeating. If we have 16 bit of data and 8 bit of key, I will repeat twice. If we have 24, I will repeat it twice. Okay. So K0, K1, K2, everything will be same. We'll just take the chunk of the data. As I said, like first K0 XOR is done, then all these circus, all these S box, P box. Then again the second time we do, again the third time we do, again the fourth time we do, then we create the cipher text. So this is one single block. That means instead of doing again and again and instead of doing it all together, we can actually break the entire key into 4 parts and we can do. That also we can do. We can do anything, right? We understood the logic. Now we are just making it more and more difficult for the attacker and the cryptanalysis so that it will give better results. So instead of doing one time XOR, I am actually doing 4 time XOR. 4 times this ASP network. Now everything is getting jumbled up. So much jumbled up, it is very difficult for somebody to find out the actual trend. Okay, so if there are maybe 1 gigabyte of data and the key size is 128 bit, all the 128, everything will run one after one, one after one. Okay, So these are the block cipher. What we learned so far, this is nothing but the block cipher. Plain text, there is a key, it creates cipher. Plain text, key, cipher text. So the plain text is repeating. I have splitted the plain text, use the same key and create the cipher text. Let us go to fine.
Unrelated question.
Mm-hmm.
You are using exactly Windows software or?
It's WSL. You just search with WSL, Windows Subsystem for Linux. Nowadays, Windows is much more advanced. You can actually use Linux terminal in Windows. Just search Windows Subsystem in Linux. You can use any Linux. You could do that on MacBook. Very easy. In the terminal, you can run any Linux command. You can run Linux. Now Windows has also come up with.
We are also.
Yeah, from Windows 10, it is no more only the DOS based. It is actually the PowerShell based. And the PowerShell, you can actually change the flavor. Even if you want, you can change it in the kernel level also. If you want, I want my entire Windows run on the Linux kernel, it will do. You can run that. So WSL2 is that it will change the kernel also. But yeah, core Windows kernel will be always Windows. That will not be changed. But yeah, that will virtualize the kernel. It will create a new kernel for you and you can run. In fact, from here you can access Windows system, Windows system 5. Sorry? Base kernel will, how you can change. Then everything will be, then probably Microsoft will have to rewrite the entire code. Okay. Created a folder. Oh, 22. Okay, I have nothing here. Let me create a file. Echo hello world. You understood what I am doing here? Anybody has any confusion that what exactly is happening?
No, ID
And hello is missing.
is also
Okay. Okay, write txt. Fine. Hello world. Now we are going to encrypt it. OpenSSL, have you guys installed OpenSSL? Okay. You can actually there you can just search. There might be some online tool as well for OpenSSL running a OpenSSL command. You can try with me also if you want to do something else. You can just try with me. Okay. OpenSSL. The command is encryption. ENC for encryption minus E. So encryption is like ENC for encryption and decryption. Both we use. Okay. OpenSSL. Hope I am right. I have not forgot it. And then minus in minus out cipher. Okay. So what does it do? OpenSSL is a suite I am using. ENC for I am trying to encrypt. It can do a lot of other things like create certificate, check certificate, verify certificate, all these lot of other things it can do. So I am using the encryption functionality minus E for encrypt and minus D for decrypt. In is the plain input file, out is the output file. Simple. Hope it will work. Yeah, perfect. It has created cipher.txt. Let us see what is written in the cipher.txt. See? Not given the key. Minus K. Just give me a hex number, any hex number, random. What we started with? The hex number D, E or some D, D and F, right? Let's use that. Okay. Old. What I am missing? Let me check. Yes, okay. Session. Okay. AES. Okay. Uh, Open SSL. Sorry. Okay. What I was missing is I have to give one more parameter, which is AES. Which algorithm, which block cipher should I use? I have not mentioned that one. Okay. OpenSSL ENC for encryption minus E. Then this is the algorithm, or this is the cipher I am using here. Okay. I am using AES. The very similar what I have shown. It's very similar to that. Then 128-bit keys using ECB. And oh, okay, I have to provide the key as well. What is that? BF. Can't open test file for reading. No such file. Okay. Sorry. I just copied it from net. Okay. I'm just using cipher. I think. Let's see. Probably it will look. Hex string is too short. Padding with 0 bytes. Fine. So it is looking for 128-bit key, right? And I have given only 16-bit. I'm coming to that. ECB, yes, AES 128 ECB. I'm coming to that. I will explain each and everything here because these are important. This is how we are implementing, right? So now if we just see, it is something different. It's totally jumbled up. And if you are like really want to do that very hectic job, you can actually try exactly the way I have shown you here. If you try with 64-bit key and do the same thing, and you have to find out exactly what is the, probably this is one of the things that they use. So you have to find out what exactly AES box and P box does. You can actually make the same output here. You can actually create that. If you do by your hand, it will be the same output. This is exactly how one will. Yeah, that if you want to do that, that is a very laborious one. Like you understood that how it works, and this is the implementation. This is exactly how all our laptop, like all our hard disk is always encrypted using AES. is encrypted. You know the encryption your hard disk is always encrypted. If it is an office laptop, it is always encrypted. Even for your personal laptop, it provides you an option. Do you want to encrypt your entire hard disk? You can do that. That encryption is always AES. Mostly AES or 3DES, but AES is the most popular. And this is the same thing. How it works? We just did it here. The XOR and this. Exactly the same thing. Same XOR, same XOR. They do. They just make jumble of all your.
So what is the difference between DBS and DBS?
Come. Survival. There are a lot of difference, lot of similarities. Now I am focusing on the similarities. Idea is clear. Now you can create your own cipher. You can, right? You can write your own cipher. That will perfectly work. That will perfectly, like you can come up with your own S box, P box. You can do the XOR. You can create your own block cipher. The block cipher is nowhere different than AES, DS, whatever. But still, why we use the AES and DS? Because it's not only S box and P box. We do a lot of other things. Okay. Fine. Now let us decrypt this the same thing as well. Minus D. Input will be the cipher. Output will be then decrypt. Okay, let's do that using the same key. Now we have plain decrypt and let's see whether it is properly decrypted or not. See, the same hello world we started. We made like we encrypted this and then we came up with hello world. And while doing encryption, we also can do, I think, encoding. How can I do the? Okay, for OpenSSL, I'm just showing you OpenSSL help. If you just ask for that, sorry, yeah, 64 encoding. I have to just check that. I'm opening the manual page for this. So OpenSSL help. There's standard command. You can use the CRL like it's a certificate request, DSA algorithm. SSL man. Okay. This is too much of text. I like the yes. Diffie-Hellman you can do Diffie-Hellman parameters, DSA, EC. Now encryption. That's what to sorry ENC for encoding with ciphers. Okay. Is a asymmetric key cryptography. Generate DSA, generate pub key. All these different things you can do. PKCS is an implementation of a suit. If you want a hardware implementation or something, so RSA and all these things you can do. Hash. So it is a complete cryptographic suite, and you can use it like programmers can use it. It is a standard one. It is in their FIPS, so no problem. It's a standard one. You can use OpenSSL whenever you want to implement any cryptographic stuff. You should use it. I am using the cryptographic, I am using the command line tool, but it has a library. You can simply call that library, be it in Python, be it in C, C++, whatever. You can simply call the library and use the functionality from OpenSSL. You are good with cryptography. Okay. And I am using the command line there. OpenSSL ENC help. Always the latest version. Always use the latest version. Yeah, base 64 is the operator or minus A. So if I want to do the same thing, and I just want to use it a base as a base 64, I can. Understood? Now if I open that Now you see it looks different. It is actually the base 64 encoded version. Okay. Okay. Any, so you understood OpenSSL? Okay, OpenSSL. What are the cipher it supports? OpenSSL BNC -L list. All these ciphers it supports. So these are the things we have heard: AES, DES, ARIA is another cipher, BF, Camellia. All these things are name of different ciphers. Okay, these are the ciphers that. Sorry, it is not there in the PPT, but if you want, I can give you. Or it's better if you can just write. I'm sharing it in the chat. I think that would be better, right? Yes, it is just OpenSSL. You can open the OpenSSL man and online everything is there. Otherwise, how I can know? I'm just sharing the comment in chat. This is for encryption. Decryption. Okay. This is for the decryption. Oh, decryption, the base 64 will not come. Sorry. This is the decryption command. Okay, fine. Now we understood that how exactly things are working. Now, any problem in this scheme? So this is exactly the AES that we have seen is like this. So this is how it is. This is how the cipher plain text, cipher part of plain text, cipher text, part of plain text, cipher text. Any problem in that? What?
No problem.
Sure. Just think in terms of OTP or one-time pad or any problem, anything that we are doing wrong that we have learned so far that is not a good idea to do what we are doing here. Okay, let's see something. Let's see. First, let us see the problem. I'm very bad at drawing, but I'm just trying something. Okay, something I just draw, and then I'm saving it. Yes. I use WSL nowadays. Actually WSL is better. But problem we had WSL1 में आपका your kernel is not changed, many of the things will not work. Just जैसे आपका if you want to run a Docker, Linux Docker will not run. Okay. Git का भी if it is Linux Git, then it will not work. But most of the common functionalities will work.
I can upload your repo from this Linux command and we can do this.
But there is Git. For Git, there are few of the things that will not work here. If you use Git, but Git pull, Git that those things will work. Git pull, Git push, Git clone, everything will work.
So that NS can also install like
Yes, 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 yes. It's as good as like your local machine only, but everything will happen inside Linux. Okay. So this is the picture I draw. See, guys, please some attention here. This is the picture I just draw, a BMP file. If I open the BMP file in the hex editor, okay, guys, this is the uh, hex format, or this is the binary format I have opened. The same bitmap file, and this is the bitmap file. Now what I am going to do, I am just going to encrypt this file. We'll see how the encrypted pattern would look like. A good encryption will destroy all the patterns. We cannot guess anything from this. Everything will be jumbled up. Now let's see if whether that really happens or not. So now guys, this is the cipher ECB file has been like this is the cipher text and there is a plain text. Now I'm opening this one. Pen cannot read this one, unfortunate. I'm doing it once again. Exactly is now see this is the cipher text. This is the cipher text, this is the plain text. What I did, I created a BMP file, simple BMP file. I encrypted this, created the cipher text. Then with a hex editor, what I did is this. It also changes the file header. The file header means this is something that says says my image viewer that this is how to read the file. This is a BMP file. BMP file has some signature header, right? Every file, be it a Word, be it a BMP file, be it a JPEG file, it has some header on that file. The first few bytes will be some header that will help identify the software whether this is the right thing or not. So I just changed the header because the header is also changed, right? So what I did, I just copied these 30 bytes, like how many? 16 into 4 byte. I have just copied and replaced with the previous one. That's why previously what I tried, I just created the cipher text, encrypted, and tried to open. It did not open because of the fact that the header was not matching. So I just replaced the header, and now I can open it with my no paint. I can open it paint. Now see the pattern is still there. Yes, but still the pattern would be there because what is happening. That's why I asked whether this has any problem or not. Does it have any problem? Because the pattern is not broken. The OTP has a problem. One time pattern. If you reuse the key, here actually we are reusing the same key. We are sending as if we are thinking like this way. The plain text we are splitting it into different 64-bit or 128-bit chunk. And for all of them we are using the same key. We are not changing the key. Key has to be changed. Otherwise that pattern will not be broken. That's why we can see even though we have encrypted with AES, the problem here is what is happening? Yep. The problem still the overall pattern is somehow preserved. Rest of the every pixel like all the values are changed, but the overall pattern is still preserved. You can figure out. But tell me why I have used AES. AES is the best encryption technology, is the standard one, everybody uses that. Still this is happening. Where I went wrong? What is the problem with that? AES is the best one. Yes, but I just use the open SSL. I'm not using my own site, but I'm using the standard site like AES. But is that possible? What you are saying is exactly similar to the one-time patch problem. You cannot have that many keys. So now, for crypto system, it is not only the cipher, the arrangement of the cipher also matters. I use AES cipher, right? But arrangement of the cipher is cipher also matters. How I am arranging the ciphers. That means that the same thing I was telling. I can do the XOR before the I can do the S box or P box before XOR, after XOR. Anytime I can do that. That is the arrangement of the cipher. I am using the same cipher, but arrangement of the cipher is different. Here, what we are doing, this arrangement is not right. This arrangement is called electronic code book. ECB, the one you asked, why I use ECB. So the command that I run here, if you remember the command I run here, AES 128, till here we understood. The thing we did not understand what stands for ECB. ECB means electronic code book. That means this arrangement, this very arrangement has a name which is called ECB or electronic code book. This is bad. AES, I have used the best cipher, I have used a good key, but the arrangement was different. So how I can solve it? Tell me something how I can solve it. How I can actually change the key every time. But I don't need to remember the key always. I will remember only one small part of it. Sorry? Perfect. You can do that. Cipher text, you just, instead of using the key, you can just send the cipher text back here. But that will have a problem again. What is that? Key will have exact same impact on all the bits. Right? That will be broken. What we can do? Does it look nice? So every time I am creating a cipher text, I am again XORing it. Then again, second time I am XORing it with the key. So I will make two XOR. Simple. I am coming to this IV. What is IV? I am telling that. But is it a good idea? Every time I am having a cipher text, I will just XOR that with the plain text and then again XOR it with the key. Fine. But every time I am doing, because this part will be always different. So I am doing 2 times XOR. First XOR will always change and it will break that. Make sense? If we do that, then show that pattern will not be there. This one is called CBC. So now remember, if I just do the same thing with CBC. So this one is called CBC. So what I need to do, I have to just replace this part with CBC. This minus ECB, I will just write it as CBC. This is the arrangement. Let's do that and let's quickly run this experiment once again. CBC, CBC. Okay. And one more thing I have to do, I am telling you that. I'm not explaining what is IV. Now let us do the same thing. We will CBC is created. I'm opening it with hex file open CBC. First 4 byte I need to. I'm just changing the first few lines of that. Now let us open. What will we see? Now see. Completely broken. Everything is fine. So arrangement of cipher matters. Previously in ECB, what we were doing, we were actually using the same key. But the smartest way, you guys only told me it's better to use the cipher text. Exactly agree there. Fine. Perfectly. Guys who are online, are you with me?
Yes, sir.
Yes, sir.
Okay. Does it is it interesting to you guys? You are following me, right? You are connecting me rather, not following me, but you can connect what I'm trying to show or what I am very excited in.
IV is a random number.
Yeah. So IV is another random number, and that might be known to everybody. No, I don't care.
Next time onwards it will be again changed.
It will be again changed, but that is not part of the cipher implementation. That is user will give, but that is not a secret. User will give just if in case you remember what I did here in OpenSSL. I actually followed this IV. I have given this IV input vector. Oh, sorry. So IV I have provided the value. If I just told anything else you can give. Fine. So it is another random number known to user, not part of the implementation. This is not secret, but you have to keep it ready for decryption. Otherwise, the decryption will not happen.
We define CBC there. We just want to complete CBC.
Exactly. Here CBC, here I was using ECBC. Perfect. Okay. ठीक है? So this is called these are different type of arrangement of the cipher. ECB is not good, we know, but in case you want to know, 90% of the 50% of the Android apps till date, 50% of the Android app uses this ECB. This is bettable.
Sorry?
50% of the Android apps still use ECB. Yes. So CBC is cipher block chaining. Cipher output and chaining it in the block. Similarly, there might be cipher feedback mode. I am coming to different modes here. It is very similar to that. Plain text comes here. So first initialization, instead of first time XORing it with the plain text, what I am doing here, I am first plain text and initialization vector. I have first started with XOR, then put it in the cipher. This time, what I am doing, initialization vector and key first I will make I will send in the cipher, then XOR it with the plain text. Make sense? Then the cipher text. So this is always different, right? Every time initialization vector is coming, key is coming. This is like this output will be, this XOR value will be different. The cipher text. I am sending the cipher text back as an initialization vector next time. The key is same. Initialization vector is different. And I really don't need to hide the initialization vector. It is a unique value. I need it during the decryption, but I don't need to make it secret, because as long as my key is secret, my encryption protocol is secret. My crypto system is secure. Perfect. Guys who are online, any question till now? It's fine, right? Should I take it as fine?
Yes, sir. I mean, in fact, we need to revisit everything over because within a day, like to
That
digest.
really I don't want. If you say that, like I hate that, because I really want you to follow me, or I want you guys to work with me so that you could you would not have to spend more time on this. But I think
We are
people
following it up. We are following it up. But
are
yeah, again,
following.
yeah, we are good with.
Okay. Okay. Please let me know if somewhere the link is broken. If somewhere you are not, you couldn't follow me. Please let me know. Please interrupt and will stop me and let me ask me questions. Okay.
Sure, sir.
Okay. And yeah, you guys followed that. What is the problem? What we tried to achieve? What was the problem? And what is the next? How we are solving that problem, right? So this is the typical walkthrough I am giving. First, starting with a problem, then giving a solution. That solution has a problem. Again, coming up with a new solution. So if you like from the very beginning, from the Caesar 2000 years back to today, I am just following the same thing. Okay, so this is CBC, then we have CFB, then we have CTR. Here, instead of initialization vector, we can do something else. A clock. Every time clock will be different, right? So we can use a counter here. So every time this is counter, we will just, there will be a value. Sorry? OFB. OFB, I have not, yeah, OFB. It's not here, but yeah, you can just simply, it's just little bit different. If you maybe I have not, then I forgot that slide I did maybe. This is OLP. So same initialization vector. So this is CDC, right? Okay. Here the WebB, the difference is that before the XOR they are taking it as a IV. Okay, that is the only difference. Here before the XOR. Like how this is different. So people have found that for different type of data, different arrangement works better.
Key remains same everywhere.
Key remains same.
We are doing some rearrangement.
So if we can do that, that's fine. We can break the pattern. That's all we need to do. We have
keeping algorithm and we are keeping the key same, but then arrangement we are changing.
Exactly.
Those 4-5 kind of arrangement.
So OTP जो प्रॉब्लम था इतना बड़ा की मुझे मिलेगा नहीं. So I need a endless key, but I don't need a endless key. I am using something other different thing so that it will generate a new key from the previous version. ठीक है? And here this is a count like CTR is I think a counter mode. That means there is a counter, so every time there is a counter increases, the different like different things come. So again it will break the pattern. Now come to another thing, crystal cipher. So far what we are seeing is a block cipher, which is exhaust cipher. Fine. Now we'll do the same thing, same S box, P box, everything will be there, but yeah, little bit different. How will we do that? First, the entire plain text will split into two. Half. Half. Then the first half we'll send the key. Then only the right part I will do the XOR. Actually, F might be XOR. F is a function, crystal function. It might be simple XOR. It might be something else also. Even there are crystal cipher which is implemented just using XOR. But most of the better crystal function use something more. XOR and or lot of other logical operators we need to, and some function, some mathematical function. So only the right side it does. Then XOR it with the left. Then again it sends the left side in the right side will come in the left. So in that, like there will be repeated round for that. 60 round, 20 round. So first left, right. So it is very much similar to that. Take a stick, 16 bit, 8 दोनों split कर दो. XOR this. Then XOR the key. Then just the right hand side send that and then again create the 16 bit. Got what I am saying? Is very much similar to this.
Okay, but
Yeah. Anyway. No.
the only thing I remember was
So far what we are doing, we are processing the entire value, entire plain text. Now what was our plain text? Remember? What was our plain text? Sorry? No, the plain text, 1010 something we have written. This one, man. Guys, you guys are following me, right? Where is that whiteboard? Yeah, 1101 1111. That's the one who started. 1101 1111. And we have a key. What is the key? 1001. What we are doing, we are just writing 1001 1001, then XOR. Good. Now these guys are saying, okay, I have a better idea. So we have this is good. This is getting nothing, but I have a better idea. What? Just split it into two. 1101 1111. पहले इस चीज के दोनों को एक करते हैं. First make the XOR of this two half. 0010. Then XOR with the key. 1011. Now take this one. 1101. Now make this one is the right, this one is the left. Then 1011, 1101. Then do the same process, follow the same process for 14 times, 15 times. Okay, but it works. Why this is better? Okay, so with the SP, like we don't need to rearrange the bits using S box or P box because ये तो actually अपने आप खुद ही हो रहा है ना. Actually, the bit patterns are actually we are breaking that. Since we have broken into two, then every time we are doing exam, we are actually breaking that connection. So we don't need to use S box or P box. We can actually using the same plain text, we can actually creating new pattern for it. And then do it for iterate it for 16 times, 20 times, 24 times, 64 times per hour. Usually 16 times are the standard. Fine. Now come to the interesting part, which is called, this same thing is called DES. The one I just showed. So now you can write your own DES algorithm. But instead of simple XOR, they use something. Oh, sorry. This is yeah. This is the S box P box is used here, but it is a crystal cipher. Okay, here I think the picture is little bit different. So actually, in DES, even with the crystal, they again use the S box and P box to make further diffusion and confusion. But actually, you may not use that one as well because that confusion and diffusion is already happening. But I just need to check whether we really need to use S box and P box here. I don't think DES use that. I will just confirm this one. Probably, as far as I remember, DES doesn't use the S box, P box because that is already taken care of. Okay, but sorry, can you? Okay, just quickly. DES I'm finishing. I'm already done. The DES already done. We all know how DES works. There we have done. So we can codify this thing, right? So just you make a codify that one, it will be DES. DES has a little bit different functions. And S box, P box probably it is not using or using. I just need to confirm. Sorry for that. Okay. Yeah, so it is block size 64-bit. Actually, it is for 3DS it is 192-bit. Okay, I'm coming to that. So it is created in 1975 by IBM and NSA together. That time it was said to be the best encryption algorithm, and it is actually uses the DE or data encryption algorithm. This crystal cipher is called data encryption algorithm. This algorithm is implemented in the crystal cipher. And it, okay, yeah, as I said, it is using expansion, mixing, substitution, and permutation. So this inside the crystal function, what I have just used XOR. With the XOR, it also uses all these four: expansion, mixing, substitution, and permutations. All these things together, they are calling this is my crystal function. So anybody can create their own crystal function. In our example, our crystal function is nothing but the XOR, but they have done a lot of other circuits as well. And it was there, but soon people found flaw in that as well. They said, okay, चलो ये भी मैंने break कर दिया. There are where mathematics, smart mathematicians, they broke this one as well. Then NSA, who was like, who thought like we are the unbreakable guys, they, because like they thought, okay, now this is not the way. This is not in a military cannot handle these things. We are good in fighting, but we are not good in mathematics. We need mathematicians only. That's why AES comes into picture. But till date, DES is obsolete, but 3DES is there. What it is? It is 3 times DES. The same DES, I will apply the encryption 3 times. And remember this one, it is a very tricky thing. In fact, for CISSP and all, this comes very often. For 3DES, there is 192-bit key are used. 190, it's little bit absurd, like not 128, not 256, it's 192. And for this 3DS, 3 times the encryption is happening. It is split into 3 different keys. And 3 times we are not doing encryption. Encryption, decryption, encryption. First time we do encryption, then we do the decryption, then we do the encryption. Then the question is, it is the same as doing this one-time encryption, right? One time I am doing encryption, second time I am doing decryption, then again I am doing encryption. That means it is a one-time encryption. So why they are saying that this is 3DS is better? No. Okay. The key is different. When I'm encrypting with one key, decrypting with another key, and again encrypting with another key. So that's why it is never the same.
When you are using different key, it will again be encrypted. Right?
Actually, it will be encrypted because it is a different key. It will not get the thing back. But why still we are using decryption? Because they found that this is much more better, much more stronger, because this S box and P box permutation and combination will be more jumblized.
I don't think they name it for
Yes.
I
Okay.
don't think they named it for better result. I think they named it for better confusion.
But if you confuse it, okay. But yeah, it provides that there is a mathematical proof. If you want, you can just search it. There is a mathematical proof why 3DS is better than DS. There is a very big mathematics
I'm
on
not
that.
saying that one.
Yeah, you are saying that it is they created to make ourselves more confused. Okay, yeah, we are confused, but attackers are also confused. That's the intention. Okay, we'll start from AES after the break. So we have 1.5 hours, right? Okay.
This is the approved word by this, right?
3DS is yes.
It's the most used.
DS is obsolete. 3DS is yes. 3DS, remember, encryption, decryption, encryption. 3 times it is happening. And decryption with the different key. Actually, all these 3 steps with 3 different keys. The same key will be split into 3 different keys. Encryption, decryption, encryption. This is standard. This you can use. This is a very, in fact, there is AES is faster. AES is more popular because AES is faster and provides almost same type of security. Okay, we'll start with idea and AES just after having the tea. And next half an hour we will spend on the ciphers, the symmetry ciphers. Then 1 hour we will spend on hash and details. Okay. You guys are finding it interesting?
Yes, sir. That is why I didn't see that till. I would have slept.
I am taking it as a compliment. Guys who are online, you are with me. You are finding it interesting. Okay.
Yes, sir. I echo what Kevin said.
Okay. So let's take a break for 10 minutes.